The last mathematical idea we want to talk about in Chapter 6 is polar coordinates. If you've had Calculus 2, you've probably already seen this, but if not, that's okay, we'll go through it. And we're just going to stick to the basics here anyway. So you're used to working in rectangular coordinates where you have x, y, where x is a horizontal distance and then y is a vertical distance. So polar coordinates, it's still an ordered pair, are theta. So theta represents an angle in standard position. Remember, standard position is rotating from the positive x-axis, where positive angles go up and negative angles go down. And r is a directed distance from the origin. So it's easier just to show you rather than to describe it. So as an example, we're going to plot the following in polar coordinates. So your angle can be in radians or degrees. Typically you think about it in radians, but I'll do some in degrees as well. So remember, the first coordinate is r, the directed distance from the origin, and then your theta is the angle in standard position. Now, usually when you do graphing in polar coordinates, you can actually buy some graph paper specifically tailored for polar coordinates, and it would look like this. So you have concentric circles around the origin. So this circle has radius 1, radius 2, radius 3. Okay, so how do you plot in polar coordinates? Well, let's plot this point A. So the theta is 60 degrees, so in standard position, you start from here, and 60 degrees would be roughly here. And then the radius is 3, so you want the point that's 3 units away from the origin on the terminal side of the 60-degree angle. So 60 degrees, the terminal side is roughly here, so 1 away, 2 away, 3 away. So there's point A in polar coordinates. Right? So rotate 60 degrees from standard position, and you're 3 units away from the origin. Okay, let's look at the second one, B. That's 170 degrees and 2 units away from the origin. So 170 degrees is almost 180, and you want to go 2 away from the origin. So that's roughly here. There's point B. Okay, the next point is negative 120 degrees. Negative 120 degrees in standard position, so it's more than here. So all the way to here is minus 180. And so it's what, two-thirds of the way to minus 180, so roughly over here somewhere. So the terminal side of that angle is here, and the radius, r, is 1 unit from the origin. So coming this way, it's roughly here. So there's point C. Now for D, E, and F, I switch from degrees to radians just to practice with radians as well. So pi over 4 radians, you know that's 45 degrees. Pi over 4 radians is exactly halfway from here to here, and we want to go 2.5, a distance of 2.5 from the origin, so 1, 2.5. So there's point D. And E and F are a little bit different. Notice every radii I've used has been positive, and now we actually have 2 that are negative. Now remember, I said that R stands for a directed distance. So when R is positive, you continue out the direction on the terminal side of the angle you started with. If R is negative, you go on the opposite side. So continue that angle on the opposite side through the origin, and that's the distance you go. So for example, 3 pi over 4, well, pi radians is to here, so 3/4 of that, 3/4 of the way puts me here. So 3 pi over 4 radians is here. The terminal side of that angle goes out in this direction in the second quadrant. So if this were positive 3/2, I would march out 1.5 that direction. But since R is negative, instead of thinking of the terminal side going this way for 3 pi over 4, you continue that angle in the opposite direction and you go 3/2 that way. So 3/2, 1.5 is here. So there's point E. Let me do that one again. So you rotate to 3 pi over 4, which is the angle with terminal side in the second quadrant here. If this were 3/2, positive 3/2, I would have gone 1.5 this way. But since R is negative, you go the opposite direction. So I go 1.5 this way. And then the last one, point F, again, R is negative. So 2 pi radians, that's all the way around. And so if R were positive, the terminal side of that angle would be on the positive x-axis, so I would move this way. But since R negative, I move the opposite direction, 1 unit that way. There's point F. Now notice one thing that's different with polar coordinates and rectangular. In rectangular coordinates, if you give me an xy, there's one point on the graph. If I show you a point on the graph, you can only give me one ordered pair xy that describes that point. But notice the point F that we just did, wouldn't that be the same point as, at least on the graph, it'd be 1 pi. If I rotate through pi radians and then move a unit 1 this way, so 1 pi would describe the same point F as -1 2 pi, wouldn't it? So in polar coordinates, there's not a one-to-one correspondence between ordered pairs and points. You can have two separate ordered pairs describing the same point, like I just did right there on F. Okay, so the next thing what we want to do, some of these graphs are very difficult to do by plotting points. And luckily we have a graphing calculator that can really help us in this regard. But I thought we would try 2 of them first just by plotting points. So let's graph each by plotting points. Okay, so the first one I want to do is the equation r equals 3. Okay, so I want to graph this equation in polar coordinates. So r equals 3. So there's no restriction on theta. Theta can be anything, but r has to be 3. Well, I don't really need to make a table to do that, I don't think. We'll just do it. So I'll stick to my concentric circles here, radius 1, 2, 3. So notice if theta equals 0 radians and r is 3, that puts me here. Right? 0 radians, so I don't rotate at all, and r is 3, 1, 2, 3. What if theta is pi over 4? Well, if theta is pi over 4, I'm here, and r is 3 is here. And if theta is pi over 2, I'm here, and r is 3, I come out here. So you see what's happening no matter where theta is, I'm going to come 3 units away from the origin, which is always going to put me on this circle, isn't it? So even if I do a negative theta, theta is negative, negative pi over 2. I'm here, go out 3 units, I'm there. So notice r equals 3 turns out to just be the circle of radius 3, centered at the origin. So that one's easy to do. I don't really need the graphing calculator to help me with that one. What if I did r equals negative 3? If I did r equals negative 3 and did the exact same procedure, notice when theta is 0 radians, I'm here, but if r is negative 3, I would march back 3 this way, which would give me this point. So if I were sketching r equals negative 3, instead of plotting that point for theta equals 0 radians, I'd plot this point. What about at pi over 2, r is negative 3, pi over 2, negative 3, instead of 3 this way, I go 3 this way, I'm here. Notice you're still going to get the same circle even if r is negative 3, because you can use any angle you want. So there's a picture of r equals 3. So a second example I want to try, just plotting points by hand, is r equals theta. If you put a k in front, a constant k out front, that's the spiral called the spiral of Archimedes. I'm just going to keep it easy by letting the coefficient of theta be 1. Again, I'm just going to do this by plotting points. So there's a circle of radius 1, radius 2, radius 3. I don't know, we'll try, I don't know how easy 4 is going to be. Okay, well, I'm just going to pick integer values to make it more or less easy. Suppose I let theta be 1, so theta is 1 radian, and r is 1. So 1 equals 1. So if theta is 1, where's 1 radian? 1 radian is approximately here. And I want to go 1 unit away from the origin, so that puts me here. So that's the point 1, 1 in polar coordinates. Now when theta is 2 radians and r is 2, where's 2, 2? Well, 2 radians is roughly here, and you're going to go out 2 units from the origin, so that's going to put me here. So that's the point 1, 1, that's the point 2, 2. I guess I could have done the point 0, 0. When theta is 0, r is 0. Theta is 0, you don't move at all from the origin. Well, in polar coordinates, the origin is called the pole. Okay, so whenever, it doesn't matter what theta is, whenever r is 0, you're at the pole. So there's 0, 0, 1, 1, 2, 2. Now where's 3, 3? Remember, halfway around the circle is pi radians. 3 is a little bit less than pi. So 3 radians is going to put me here on the terminal side here, and I'm going to go out 3. 1, 2, 3. So that's putting me here. And if I did 4 radians is going to put me down here somewhere, right? If you keep going 4 radians, and then I'm going to be 4 away, so roughly there. Now you see what's going to happen. As I rotate around, my point gets further away from the origin. So this is going to do something like this. Now I picked integer values. Remember, theta could be a half, 0.2, square root of 2. They don't have to be integer values, but I picked integers just to make it easier to plot. The angles were more complicated, but finding them away from the origin was a lot easier. And this is just going to keep going. That's why it's called a spiral. Now, this is not the entire graph. You have to be careful here about picking, just positive integers when you're graphing things. What if theta is negative? For example, what if theta were -1? If theta is -1, then r is -1. So if theta is -1, I'm down here. My angle's down here. But if r is -1, I don't come out this direction. I back up and go this direction 1 unit, which is here. Now, what if r and theta are both -2? Well, -2 radians puts me roughly down here, but instead of going 2 this way, r is -2, so I have to come back this way, and that puts it roughly here. And then when -3 radians is almost to here, almost to the halfway point at pi, negative pi. So -3 radians is here, but instead of coming 3 this way, I'm going to extend back and go 3 that way, which puts me here. And so you see, you also are going to spiral the other direction. And that just continues on. So the -4 is going to be here. Okay, so it spirals in both directions. So if you only take 0 and positive values for theta, you're only going to get half of the spiral. You have to allow theta to be negative as well. So that one's not that hard to plot by hand. Now let's do some with the calculator now. And you may not have had any experience doing this, so if you have a TI-83 or 84, you ought to be able to play along. So example. Graph using the calculator. We'll just do a few of these. For example, let's sketch the graph of r equals 3 cosine theta. So if you have a TI-83 or 84, if you do, I'm sure you've done a lot of graphing with it. If you go to y equals, you're not going to be able to do this because it says y equals, and when you type in variables, it's going to give you x. It's going to treat it as rectangular coordinates, which you usually use. If you want to do a graph in the polar coordinates, you have to change the mode on your calculator. So again, if you have the online version of the 83 or the 84 that I sent you in an email, if you go to the mode, right, which is next to the second button, the mode. If you go to the mode, the fourth choice down says func. That's for function, the usual one you use. If you have to scroll down, change func to POL for polar. So if I scroll down and move over and then hit enter, I don't know if you can see this very well. You change it to POL to polar and then hit enter. Now if you go back to y equals, it says R1 equals R2 equals. So now it's expressing it in polar. So if you've done that, again, I don't know if you can see that. It says R equals. So we can type in 3 cosine theta. So 3 cosine. Now where do you get the theta from? Well, where did you get the x from? The button where you always got x, it says xt theta n, the button that's right there, right? Xt theta n. If you hit that now, it'll put the theta in instead of x. Okay? So let me close out that parenthesis. So now I have R1 equals 3 cosine theta. Now you have to be careful here. If you go to window, okay, so the window button is up here next to the y equals, right? See the window button? So the window button, notice you have a theta min, a theta max, a theta step. an x min, an x max, an x scale, and a y min, a y max, a y scale. So the x and the y works just like the window when you graphed with y equals something with x's. So x min, x max, y min, y max. But we have this extra variable theta min, so you have to tell what's the smallest theta you want to use, what's the largest, and how often do you want it to scale through the thetas. So for x, let me jump down. For x min and x max, I'm going to use -4 to 4. So horizontally -4 to 4, and I'm going to leave x scale 1, so a tick mark every one. For y min, I'm going to use -4 and 4 for y max with a scale of 1. So that's, -4 to 4 this way, -4 to 4 that way. So same as usual. Now, what do we do about the theta? What I usually do, and you can always modify it later, theta min, I usually start with 0, and theta max, I use 2 pi. Now that's basically getting you one revolution, 0 to 2 pi like we did before. So 0 radians all the way around to 2 pi. Sometimes that's not enough. But it's just plain old theta here, so going from 0 to 2 pi hopefully is enough. If it's not, change it to -2 pi to 2 pi, or if you have a coefficient in front of theta, you may want to change the scale. Like if this were half theta, if you went theta 0 to 2 pi, half theta is only going 0 to pi overall, so that may not be enough. And then the real important thing is the theta step. So I told it to start at theta is 0 and go to 2 pi, but the theta step says once you start at 0, how much do you add to that to plot another point? If theta step is too small, if I put 0.0001, it's going to start at 0, then 0.001, then 0.002 for theta. It's going to take forever. It's plotting way too many points. If you make theta too big, for example, on this one, if I let theta step be 1, notice I'm telling the calculator to start with theta 0 and go to theta's 2 pi, which is a little over 6, and add 1 each time. So it's going to plot 0, 1, 2, 3, 4, 5, 6. It's only going to plot 7 points, and then connect them. If I do that right now, oh my goodness gracious, it plotted it like a triangle, a couple of triangles on top of each other. That's not what it looks like. Okay, so when you do your window, theta step, I don't know, if I do 0.1, I don't know, that's going to be several hundred points. That may take a while, but I'm going to try that. So if you hit graph, right, the graph button over here, let's see what it looks like. Well, that's not so bad. It actually is going, it plotted and then went back over it, so it made a bold-faced line. It did it twice. Again, I don't know if you can see that, but it looks like it's a circle-ish. It looks more oval than circle. But the problem is your graph on the TI, I have a TI 83 Plus, it's more horizontal than vertical, right? The screen is more horizontal than vertical, and the calculator is not adjusting for that. If you want to get it to square that out, if you go under zoom instead of graph, if you hit zoom, which is the middle button here, zoom number 5 is Z square, it balances out that extra horizontal on the screen than vertical. So if you hit number 5, the Z square, it'll graph it, it'll adjust for that, and notice now it looks, if you can see, it looks more like a circle. Okay, so the graph of that, the graph of this one, it's a circle. Oh, that's not very good, but that's what it looks like. It's a circle. Okay, let's do another one. What if we do the r equals 2 sine theta? Well, notice the coefficient here is 3. I mean, no, the radius isn't 3. It looks like the radius is 1.5, but my diameter turned out to be 3. If this holds the same sort of flavor, then maybe my window is perfectly fine. I don't have to adjust it. I'm just going to hit graph and see what we get, and hopefully, oops, it'd help if I type in the new equation. Go back to y equals, and you have to type in 2 sine theta. And I'm just going to hit graph and hope that this window works just as well. And it's looking pretty good. And it's stuck to the square window I had before, I believe. If I do the Z square, yeah, it looks exactly the same. Okay, so this window turned out to be perfectly fine, but notice that this circle is is more vertical, that one's more horizontal. So the diameter of that circle turned out to be 2. So a multiple times cosine, a multiple times sine, turned out to be circles. Let's do something a little more elaborate. Let's try C here. R equals 4 sine 2 theta. Okay, 4 sine 2 theta. If you're using the calculator, why don't you pause the video, see if you can get a decent graph of that. And then I will do it, and we'll see if we get close to the same thing. Again, you may have to play around with the window. The window we've been using may not be so great on this one. So stop the video and see if you can do it. Okay, so if I go back to y equals and type in 4 sine 2 theta, I'm going to try the same window we were using and see if oh, yeah, I just hit graph and it's looking pretty good. Looks like we're getting a 4-leaf clover sort of thing here. Looks like we have a leaf there and a leaf there. I'm not really concerned about this. Oops. It's a little lopsided, but you get the idea. Just out of curiosity, if I go back to y equals and move down a line and type in R2 equals 4. So I'm going to plot them both and see what happens. Notice if you do that and plot them together, this graph, if you plot the R equals 4 underneath it, you get a circle of radius 4, which does not surprise you based upon the example we did before with R equals 3. And this sits right inside that circle of R equals 4. It looks like a sand dollar when you put them together. So a logical question, an obvious question is, well, we have 4 leaves in this picture. Is that from the 4, or does it have something to do with the 2? Well, let's pick a different example, example D here, and let's plot -2 cosine 5 theta. R equals -2 cosine 5 theta. Let's try that one. So I'm going to clear out both the ones I did before. -2 cosine 5 theta. So we'll see what happens with this one if our conjecture there works. I'm just going to use the same window. We can change it if we need to. Yeah, it's a little small, but you can see what's going on. So again, I'm going from 0 to 2 pi in every single one of these. So this one, it looks like you have 5 little leaves here. So you have a leaf here, and a leaf up here, and a leaf that straddles the axis, and another one here, and another one here. I know that's ugly, but that's roughly what you get. So is this? It's hard to see the scale, but this was sitting inside the circle of radius 4. Is this one sitting inside the circle of radius 2? If I go back to the y equals button and type in R2 equals 2 and hit the graph, yes. If I graph R equals 2, this sits right inside. So these are touching the circle R equals 2. What if I do something a little more elaborate? So the last example we'll do here on the calculator. Example E, I say R is sine theta plus cosine theta. Let's try that one. So if I go back to R equals and clear out the ones I've already typed in, sine theta plus cosine theta. Okay, this is way too small I need to change my window. I can't see what's going on. It's scrunched up just right here, so I have a window going from -5 to 5. So what if I change my window for x min -2 to 2, and the y's go from -2 to 2. I'm going to leave theta from 0 to 2 pi. That's much better. I messed up my window, hold on. not super accurate here. Let me change it one more time. If your calculator keeps thinking when it's graphing and you're getting impatient and maybe your theta was too small, as it's graphing and the little thing is running over here, you can always hit the on button to pause it, to stop it, and then you can go back and change something. So you can always hit the on button to get it to stop graphing. Let me play with this window one more time. I'm trying to get a really good picture here. Okay. I change it from x is -1 to 2 and y is -1 to 2, and it looks like an oval here. Let me see if it's actually, if I go to the z square, see if it actually is a circle. Yeah, when I do that, it looks more like a circle. Like that. And again, you can play around, change the number here, change the number here. Notice the 5 here gave me 5 petals. The 2 here gave me 4. Is that always going to be true? Notice with the sine and the cosine is different. So change numbers here and change numbers here and plot a few more and see if you can tell what's going on. Now something that might be useful, it's fine to work in polar coordinates, it's fine to work in rectangular coordinates, but what if you want to go from one to the other? So that's what I want to talk about next. So how do we do conversion from one unit to the other? It's very simple if you just think about your standard picture that you learned in trigonometry or pre-calculus. Right? Again, I'm going to draw this in the first quadrant, but I could have done it in any quadrant. So imagine you have an angle theta here in standard position, and you have a point out here. I'm going to call this point x, y, just in our rectangular coordinates. So if you make a triangle with a right triangle with a vertical line here, there's x and there's y, and typically you call the length of the hypotenuse from here to here, the distance from the origin to the point, as r. Well, notice in my picture I have both x and y and r theta. You can see that this point xy in rectangular coordinates is the exact same point as r theta in polar, because I'm rotating through theta and moving out a distance of r. I'm assuming r is positive here. So what's the relationship between these? Well, suppose you knew, how would you go from rectangular to polar? So suppose you knew x and y and you were trying to figure out r and theta. Well, if you know x and y, you can get r very easily. This is a right triangle. So r squared would be x squared plus y squared. Just use Pythagorean theorem, you can find r. And if you knew x and y, how do you find theta? Well, the easiest relationship, you could say tan of theta, tangent is opposite over adjacent, or the y over x. So that's, if you know x and y, this will help you get to r and theta. Now you have to be careful if you're in a different quadrant trying the first, besides the first with the theta. Okay, now what if you knew the polar and you were trying to go to rectangular? Right, so if you knew theta and r, how could you get x and y? Well, let's see. Well, what's the sine of theta? Notice sine of theta, remember that's opposite over hypotenuse, or y over r, however you memorize that. Sine of theta is y over r. If you multiply both sides by r, you get y is r sine theta. So if you know r and theta, you can get y. And likewise, cosine theta is adjacent over hypotenuse, so that's x over r. Multiply both sides by r, you get x is r cosine theta. So if you know r and theta, you can get your x and your y. Frankly, I don't memorize that. I just draw a picture of, if I know xy, I draw the picture with xy. If I know r and theta, I draw that and just use trigonometry to figure out the others. I don't memorize these formulas. I just use my trig to figure it out. Let's do an example. Convert the equation. R is 3 cosine theta to rectangular coordinates. Now, when I say convert, that means get rid of the r and the theta and replace everything with just x's and y's. Well, from what we just did, r squared, so we know r and theta, but notice r squared is x squared plus y squared. So how do we get rid of the r? Well, r is the square root of that. In fact, it's plus or minus square root. But replace the r, that r here is plus or minus the square root of x squared plus y squared. So that's no problem. And we probably could have made it a little bit nicer to start with, now that I think about it. But on the other side, well, without even going to this step here, right, what's the cosine of theta? Cosine is x over r, right? So I can replace the cosine with x over r. And I still have that x though, don't I? I need to get rid of that. No, I need to get rid of the r, sorry. Yeah, okay, so the r on the other side, okay, if you want to do that. Like I said, I'm making this one too hard because I wasn't trying to look ahead. So this is 3x over, again, r is plus or minus the square root of x squared plus y squared. So what I could have done from the beginning to make this a little bit nicer, let me just go ahead and do that now. Again, I don't try to look 8 steps ahead, I just kind of see what's going on. What we could have done to start with, I'm going to erase this. What we did is perfectly fine, but now that I see what's going on, let me just do that first step anyway. Cosine was x over r, so I can write that as x over r. Now if you multiply both sides by r, you get r squared is 3x. And notice I don't have to worry about the plus or minus on that r, because now I have r squared, and r squared is x squared plus y squared. So that makes it a little bit easier. Sometimes it's easier to leave just the r in there until you actually get down to the nitty gritty. And if you just have an r, you can replace it with the plus or minus. Now if you want to solve for y here, you could. So y squared would be minus x squared plus 3x. And then y would be plus or minus the square root of minus x squared plus 3x. Now be careful. Don't say, oh, there's a negative there, so what's under the radical is going to be negative. Well, it depends. Depends on what x is. If x is, say, a half, notice you're going to have 3 halves minus a fourth, which would be positive, so you're okay. Notice if x is, 7, you're going to get a negative radicand, so that's no good. And the only reason, this is perfectly fine as an answer, to be honest with you, but if you wanted to type this in your calculator to see what you get in rectangular coordinates, this is what you have to do. You have to solve for y. So to put this in the calculator, you'd have to put in y1 equals positive root, and then y2 you'd have to put negative root, because this is not a function. Y is not a function of x here, so it's actually 2 functions pasted together. You'd have to type it in this way in your calculator. So notice that this one's a whole lot easier to express as an equation in polar coordinates than it is in rectangular. That's sort of the point. Let's do one more like that. I want to go back to the example we did before. So example, the one we grabbed before. Convert r equals theta to rectangular coordinates. Okay? Well, we already discussed, we know that the r is plus or minus the square root of x squared plus y squared. So we already know that's r. Now how are you supposed to get that theta? Well, remember we had before that tan of theta was y over x. So theta is going to be tan inverse, arctan, of y over x. So now solving for y is not going to be a good proposition here. That's a mess. But that's the whole point of this exercise, to show you it wasn't that difficult to sketch a graph of this. The spiral of Archimedes, where the coefficient was 1 in front of theta, we plotted that by hand and we could see what was going on. But if I gave you this and said sketch this graph, I wouldn't even know where to begin with this mess. So that's the point. Rectangular coordinates, might be better, well, not even here, might be better in some examples, but polar coordinates, using that is a lot better to work with than say something like this. And if you've had Calc 3 or you're going to be taking Calc 3, you'll see that, because you're going to, this is a coordinate system in 2 dimensions, you're going to add something to it to go to 3. So when you do this in Calc 3, you'll see a lot of interesting 3-dimensional graphs you get are much easier to describe with polar coordinates in the plane than it is to use rectangular coordinates. So these few problems should get you through the rest of the homework in Chapter 6.